Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and we're now going to look at the angular momentum operator in its role as an effective potential. This is going to proceed from applying some of the commutator identities that you derived in the previous part. So again, what we're doing here involves a fundamental derivation, and I just have to emphasize, if you really want to benefit from this course and learn something, practical, both about quantum physics and with a lot of applications to other types of analysis, you have to work it out. I mean, I can't force you to, but it's a time to decide whether it's worth your while or not. I'll have to say that I think that when you complete this derivation, you will have done something foundational, and you should see that it has implications for a lot of other physics problems that you may have been working with in your career: electromagnetism, acoustics, wave motion, and the like. Okay, so I'm just going to keep before you the various identities as fundamental things, which we started with, then things that we proved together or you proved offline, and I'm just going to try to keep these visible and in mind so that you can get the results from that we need. The most important thing that we're going to do in this part is to show the relationship of the angular momentum operators, the L squared, to the kinetic energy operator. Now, you might anticipate that there is such a thing, because after all, L squared looks like this, and this is R cross P, so there's a P squared lurking in there somewhere. Just how does that work out? Well, once again, we have here's the first. Well, here are the two components of the scalar product, and I've taken the minus sign of the h bar squared outside just so that we're dealing with something that just has the x's and the p's, and okay, and dq is the expression for, just in case that's unfamiliar to you. Just helps simplify the notation. Okay, so now we can pass through the Levi-Civita, and we're now back. Now we have the contraction identity because we're summing over these common indices I that came from the scalar product. Came from that scalar product, and now we apply the contraction identities to these here. So in other words, this is just a straightforward compression of that symbol, and then we're going to reduce this further by using this identity to move the x out from behind or out from in front of the derivative. Okay, so there's very little point in trying to follow a fast-paced derivation there, but starting from this, you should be able to derive this identity, which shows that the angular momentum is linked up to the kinetic energy in a rather profound way. So just to express that in a more familiar form, let's take the Hamiltonian for the motion of a particle in a fixed potential. And now we see the kinetic energy can be written in this form, where R is R in our notation is like XA, XXA. XA, square root XA, the usual radius. So we get, we didn't actually transform to spherical coordinates, but there's a very natural development of the expression of the square of the kinetic energy, the square of the angular momentum operator, brings us to this form where the kinetic energy is now expressed naturally in spherical polar coordinates, with L being an operator that acts in those coordinates. So that's how angular momentum enters the Hamiltonian. Thus, if you think about where this came from, anytime you have an equation with a Laplacian, you have something that's very much like an angular momentum, though it may not be described in those terms. So the various multiple moments of electromagnetic field correspond to correspond to angular momentum. The same things in acoustics and fluid mechanics, and a lot of the analytical techniques that will develop for understanding L squared have applications in those areas as well. The other very important point about this, I say that angular momentum is more powerful than gravity. Well, gravity is pretty powerful, but this basically we get a V effective, which is proportional to L squared over R squared. So this is one of these. This is this inverse depend. This is it's part of the kinetic energy operator, and in the variational methods section, we saw that short distances correspond to high kinetic energy. So basically, the angular momentum presents a sort of an effective potential for to particle motion that is repulsive, inverse square law. And I'll just note that there's a further generalization of this type of approach can be made to an n-dimensional system. And we're not going to do that here, but it is something that is used in practice for nuclear physics, molecular collisions, and sometimes atomic physics. It is sometimes advantageous to have a fully symmetrized system of coordinates, includes all particles, and then one gets some implications about short-range behavior of those systems from looking at the thinking of the generalized angular momentum as an effective potential. Okay, so now we're going to conclude this lecture with the description of the relationship between the angular momentum and the Runge-Lenz vector that was discussed in the earlier lectures on the hydrogen atom. Hope to see you then.